Well, let's do a quick example or two on using these thick lens formula, locating the principal points. And this particular one is given here. I just pulled this out of an optics book, old optics book that I had. Um, a convex lens has a thickness of 4 centimeters and a radii of curvature of 6 centimeters and 10 centimeters. And we need to find the front focal lengths, the back focal lengths, the focal lengths, the location of the principal points, and we're given that the lens glass has an index of refraction of 1.5. We're not told whether it's what media it's in, but since we're not told, you can assume that it's air, which is the most typical case. First thing we have to decide is, well, what exactly is a convex lens? and when people say convex lens, it means that the surfaces are bowed outward from the center of the lens on both sides. So it's a lens that has this shape, and I've given a big thickness here. But R1 is the radius of curvature of the front surface, and R2 of the back surface. And the magnitude is given for both of those as 6 and 10 centimeters respectively for R1 and R2. Um, we have to honor our sign conventions, remember, and remember that the radius of curvature for these convex surfaces like this is positive, and so R1 is positive, but this one is curved the other way, and that's really a concave surface, and so that's a negative, and so we enter R1 as 6 centimeters and R2 as 10 centimeters. The the thickness is 4 centimeters, and so the distance between the front vertex and the back vertex is 4 centimeters in this particular problem. And the first thing I do is simply compute the refractive powers of both of those surfaces. Remember, P1 is n minus n1 over R1, and that's 1.5. That's the index of refraction of glass is 1.5 is given, minus 1 divided by this radius 6. And when I do that, I get 1 over 12. I've started to write that out as a decimal, but I didn't go ahead and do it. Yeah. And P2, again, I can do that as well. Remember, it's is N2 minus N over R2. N2 is 1. That's whatever the index of refraction is over here, assuming air. And N is 1.5. And R2 was minus 10 centimeters. And so that becomes a positive minus a half from 1 minus 1.5 and minus 10, so 1 over 20. In this particular case, this is a case where we have air on both sides, and so in this case, from our previous discussion, we know that this formula reduces to F2 is minus F1, or F1 is equal to minus F2, and that's which I'll indicate by F here. Yeah. So now we're really ready to start the problem. We've got things set up, and first calculate F2. So I calculate F2. It's 1 over F. So I'm using this for F. F2 is F. Is 1 over 12 centimeters. That's P1. 1 over 20 centimeters. That's P2. Minus the thickness. 4 centimeters. Again, P1, P2 are 1 over 12, 1 over 20. Divided by N. And then when I punch those into my calculator, I get 1 over F is this number. And when I reciprocated both sides, I get that the focal length F2 is 8.18 centimeters. And if that's the case, then F2 is F, and F1 is minus F2. And so F1 and with our sign convention is minus 8.18. So F2 8.18 centimeters, F1 minus 8.18 centimeters. And now we're in a position where we can calculate script F2, the back focal length. We've got F2. We know these other quantities. So again, F2 was plus 8.1, 1 minus the thickness. P1 was 1/12, which was 0.08333 inverse centimeters divided by index of refraction. And when I did all of that, I got 6.36. Notice I'm in a position now that I can, in fact, write both of those numbers. From F2, I know that it's positive, and so from this vertex, 6.36 centimeters in a positive to the right direction is the secondary focal point. Moreover, I know that the secondary focal length is 8.18, and if you look at it, you can really figure this out. But basically, what I call little h2 is a script f2 minus f2, and when you do that, you'll get h2. Well, I did that here. 6.36 minus 8.18, and I get a minus 1.82 centimeters. So from the back vertex, negative is toward the left, and the negative x direction along the optical axis, that locates the secondary principal plane, in particular the point H1. Well, you can do a similar thing for the front. Notice I don't really have to calculate the front focal length. I already have that from up here, so I don't use really the formula in terms of P1, P2. I just use its relationship to F2. But the primary focal length is minus 8.18. It's just the negative of the secondary focal length. Once I have F1, then I can get script F1, knowing P2, which I had earlier. And if you look at that, F1 is minus 8.18 centimeters. T is 4 centimeters. P2 was 1/20th positive, which is 0.05 centimeters, divided by N1. And if you multiply all that out, you get that script F1. The front focal length is minus 7.09 centimeters. Notice it's negative, and so it's this direction, and it always locates the focal point. So to the right is positive, to the left is negative, our sign convention. And F1 likewise is negative. Again, you could, from a knowledge of script F1 and F1, minus 8.18 and minus 7.9, then you can get H1. But I usually use the formula. H1 is script F1 minus F1. And if you put both of those numbers in for script F1 and F1, you get a positive 1.09. Positive is, again, from the vertex, locates the front principal plane. So everything's located. You can separate them out. Sometimes I find it easier to separate out the front and the back portions and draw them separately. Sometimes it gets a little bit busy depending on the diagram and the lens. But that I think gets us everything. What else did we need? We got the front and the back focal lengths. That's F1 and F2. They're just negatives of each other. We have the front focal. We got the front focal length, that's script F1, and the back focal length, that's script F2. And then C, we got the focal lengths F1 and F2, which are negatives of each other. And we're able to locate the principal planes for this that's indicated in the diagrams. Well, that's a pretty typical example of applying those formulas, and probably one of the easier I'd say pretty typical. It's not really easier or less easy or harder than others.